And that the semester's done at that point. Your grade's set at that point. Another thing, what we're going to do is just give you information. Just give you basic information that help you with your project. And everybody will have the same information to go off of. And so as you contribute to your group, you can talk about this information and how it plays in to your project that you're going to do. So we're going to have you find periodic trends. A periodic trend is a pattern either going across a period or going down a group that you see occur based on a spreadsheet of information. So tomorrow or Thursday, you're going to get this big spreadsheet of information. And I'm going to show you how to manipulate that spreadsheet to help you isolate groups and periods. Okay? And there'll be a bunch of just numbers based upon a characteristic that we see in atoms. How they bond, how they lose electrons, how they gain electrons. That's all important in forming a compound, which we're going to eventually get to. There's a couple characteristics that you guys will probably use in your discussion of a reason why a certain behavior you think happens the way it does. Okay? An explanation to a phenomena that's happening. Okay? So we're going to have a phenomena that we're going to look at. A phenomena is just a naturally occurring event, and then looking at that event and explaining that event. Okay? And then that's kind of what we're going to do today with atomic radii. So the size of the atom, how does it change going down a group on the periodic table? How does it change going across a period? Size of the atom, how big or small it is. Okay? So we're going to look at that phenomena. So that's not be one you can use, but that's an example I'll share with you so you can kind of see what you're getting yourself into when you do this activity. Okay? So a trend is something that is something that happens going across or down a column. All right? We're going to look at atomic radii today when we do that. Questions on trends. How about you guys, trends in fashion and that? Do you guys have any, is there any trends in fashion like this Christmas? I'd like this under the Christmas tree because everybody has one. Is there anything that's... Mine was Atari. You guys remember? You guys know what Atari is?
Oh, yeah.
Mine was Atari. It's like, I want an Atari. Okay? And at that time, the graphics in that were terrible. But we thought they were pretty cool. You play football and you have three men and a running back. And the three men would shake. Do you ever play that? And they shake, you know, and you move them down the field and you try to break free and not get tackled. That type of thing. But is there anything that you guys, under the Christmas tree, that would be cool to have? Any trends on clothing or... Huh? You guys don't want anything for Christmas, right?
We're just such a
You want money?
class.
Huh?
We're just such a grateful class.
Yeah. Well, what? So, you probably tell your parents, you know, this would be really nice to have on Christmas morning. I'd really like one of these, or have this. They probably ask for information, don't they, from you, so they can do a good job of getting you a gift, as long as it's not too costly, right? Okay, because otherwise, if they don't have a hard clue and they give you money or gift cards and that type of thing. So, the first thing I'm going to share with you is this. This is a definition of something that you guys will be using later on, and it's called the atomic radii. This is how they figure it out. But before we do that, you guys don't have to draw this out. When I give you guys information, I'm not including the middle group. I'm not including the Ds. And the reason why the Ds are never outer shell electrons. So when we look at all these characteristics that you guys will have to come up with for trends, and you'll see what a trend is here in a second, you're only going to look at main group elements, because we're only going to look at the elements with electrons in their outer shell. The D shell, okay, or the sub-level, are always in inner levels. They always go like 4s, 3d. Okay, so it's just the 4 S's we look at and the 4 P's, not the 3 D's. Okay, so we're not, or the F's. Okay, we didn't even do the F's. So we're only looking at main group elements. When I give you guys a spreadsheet, it's groups 1 and 2, group 13 through 18. That's all I'm giving you information on. So when we look at a period trend goes across. Okay, period trend would be going across. So the period trend would be going here, looking at values of some different characteristics. That's a period trend. And we're talking about a group trend, then it's going down. So group is we're looking down, period we're looking across. And it's only the main group elements that we're looking at going across. Does that make sense? We're not looking at D's or F's, we're eliminating those characteristics for right now. Okay, so the first definition that you guys need to know a little bit about so that you can explain it when you have to is called the Atomic Radii. And this is the definition. This is an example of looking at the definition. And this bottom part, you don't have to write down. So this bottom part, it says group trend for atomic radii. We're going to look at that on your periodic table. So this bottom portion, you don't have to write down. So that makes it a lot easier. So you guys are writing it down. What they do is they take 2 atoms side by side that are like in a regular crystal structure, and they, in a roundabout way, they figure the distance between the 2 nuclei of those 2 atoms that are together in a sample, and they cut that in half, and they say that's the size of the atom. So it's relative to the size of the atom. So we know the bigger the radius of a circle, the bigger the circle. Okay? So in this case, we know half of the distance between 2 nuclei of 2 identical atoms is going to represent the size of the atom. Okay? It's going to be the radius of the between the nucleus and the outer portion of the atom. So that has to do with the size of the atom. So we're going to look at 2 trends today, a group trend and a period trend for atomic radii. And we're going to have to come up with an explanation. You guys are going to help me with the explanation. And that's what you're going to have to do when you have a certain trend you're going to be looking at as well. Okay? Now, you guys get to choose your trend. And if you see one that you kind of understand, you see a trend associated with it, then you can pick that trend. Not all of them work as good as the period trend or atomic radii. Atomic radii is pretty easy to see. Some of these others are a little tougher to see. By the way, when you're done with doing your activity, you're going to put it on this board. You're going to have all your information on here. Everything on here to prove your point. Okay? You're going to have a top title, what you're looking at, atomic radii. Okay? Down here, the second thing I'd write down is I'd say the group trend for atomic radii is to, we're going to go over that here in a second. Okay? And then I might have a data table that I write out. I might have some pictures that I write out, something like similar to that. You know, that helps me explain. Those visuals help explain my reasoning. And then the last part would be your argument. Your reasoning, your argument, why that trend happens the way it does. Okay? And argument doesn't have to be right. But it has to make sense. You have to be able to take that argument, use the data, use some information, and to the best of your knowledge, it makes a lot of sense. Okay? It's logical. Okay? And you'll find out most of your reasoning is going to be spot on. Okay? Because you guys can talk as a group and then confer with one another and say, hey, that makes a lot of sense. And you say, no, that doesn't make any sense. That doesn't. There's no logic to that. That's just kind of random, put together stuff. And There must be a better way to explain this trend, what's happening. Okay? Something really important that you guys will probably use in your explanation of your trends has to do with this thing called Coulomb's law. I'm going to give you a little bit at a time. So this is the equation for Coulomb's law. Okay? Coulomb's law is a way to measure a force between two charged particles. It's the way to plug it into an equation and to measure a force between two. The only thing I left out of here that I need to include is a K for a constant. And I'm going to put it in right here. Okay, so I'm going to erase my minus sign. I did this for the first period, but the second period I rewrote it and didn't include it, and I need to tell them I need to include that because I don't want to lie in the process of showing this. So you'll have a K up here, and that K is Coulomb's constant. So it's a value, just kind of like the last couple calculations or equations that we had a constant dealing with where we had to do a calculation. But it doesn't have any variance on how the Q1 and Q2 and the distance, how they all kind of compare to one another in the definition. This force is N, what do you think N stands for? Newtons. So that N is newtons, and newtons is a way to measure force. And then this would be equals, of course. That whole thing equals. So let's just get some real general information out of this that you guys know. If we have a positive and negative like I have shown here, will these two particles be attracting one another or repelling one another? Okay, you guys know that. That's a basic law of information. If two charges are opposite of one another, they'll attract. Okay, so we know that. So we know. But if this was a +1 here and a +1, what do we know about those two particles? They repel. There'll be a force pushing them away from one another. There's a repelling force. So this force could be attracting or it could be repelling depending upon your charges that you're comparing. Does that make sense? Okay. So, I'm going to ask you some questions. So let's say that this Q1 and Q2, we have a certain distance and we calculate a force. Let's say that what we're going to do is we're going to double. Okay, well this was a -1. Okay, let's say this was a -1. Now what we're going to do is we're going to change it to a -2 charge, or double the negative charge. So now the charge is double of the negative. And the positive one stays the same. The distance doesn't change. How does the force change? Does it go up? How many think it goes up? The force increases. How many think the force goes down? Got one in each. How many? Two. How many think it doesn't change whatsoever? Okay? Okay. So, I doubled this charge. Okay, this charge stays the same. This distance stays the same. So if I double the charge, what happens to the force? It goes up. How much?
-1.
Doubles.
That's right.
Okay? It doubles. Now this force, you say the sign, well that's a negative, but this charge doubled its original charge. And so the attraction force between the two will double. Okay? It's double the amount that this one. It could be double the negative value. It doesn't matter. It's still double. Alright? Let's say that we would go ahead and double this charge here, and we say, now we're going to double that charge, what happens to the force? This doubled, and this doubled, okay, according to the original -1 and +1, this force would be how much bigger? 4 times bigger. Because it was 1 times 1, now it's 2 times 2, which is 4 times bigger. I mean, it's that easy. Okay, it's that easy. So, what happens to the force as we get, now what do you think the +2 represents in an atom? Right, positive charge ion, it could. But within the atom itself, what's positive within the atom itself? Protons.
Wait, there are 2 now?
What's that? No, I'm just asking you what's positive in the, everybody that passes chemistry, I hope goes out of here and they ask you what the charge of the proton is, you don't say negative. And you don't say neutral. But you say a proton is positive and an electron is negative. So this represents could represent protons, right? And this -2 could represent 2 electrons. This could represent 2 protons. Okay, that'd be like helium. Okay? So, that is, what kind of relationship is that when you change a value of one thing on one side of the equation and the other side changes the same amount? What kind of, in math, what kind of relationship is that? Direct. Direct proportion. Double this, left side. Goes up 4 times, left side goes up 4 times. It's directly proportional. Okay? Now we're going to throw distance into this equation. So we're not going to change the variable Q1 and Q2 anymore. We're just going to have those, we did the original, +1 and -1. Let's say that we change this distance and we make it half the distance, which means we take these particles and we decrease the distance to half the original distance. What happens to the force of attraction between those 2 particles? How many think that the force will increase? Raise your hand. 1, 2. Okay? If the distance between 2 particles here, okay, +1, -1, we cut the distance in half. What happens to the force of attraction? Does it increase? How many think it increases? Raise your hand.
Gravity works this way. I guess I know something.
Okay. How many think it decreases? How many think it remains the same? Okay. Those who raise their hand, it does increase. Now tell me, if you're really good at knowing this, how much does it increase when we cut it in half? How many think it doubles? How many think it goes up more than double? Okay? Now, if we take a half and square it, what does it become? 1/4. If we take a value that doesn't change divided by 1/4, how does the force change? How much does it go up? 4 times. So it doesn't double when you decrease the distance. It goes up 4 times. Alright? If we make this 1/3 the distance, what happens to the force of attraction between the 2?
3 times as much.
You would think 3 times, but 1/3 squared is 1/9. So we got a value that's 1/9 dividing into the original number, which makes it 9 times. It's that inverse relationship. So we call it an inverse relationship. So you guys can see how distance really affects attraction between particles. You double the distance, then the force is cut in 1/4. We actually make the distance double, now the force is 1/4. So the attraction between the particles becomes much, much less. Okay? And gravity works the same way. Okay? Gravity works the same way, because this would be mass 1, mass 2, and this is the distance between 2 objects. Okay? So what I'm going to do is I'm going to give you that definition. All right? It starts it out. It doesn't do the full thing because I don't want you writing. So it says the magnitude, how big the force is. It has to say electrostatic force because it can't be gravitational force. So it has to be electrostatic, dealing with charges. The magnitude of the attracting force or repelling force between two charges, 2 points, charges, or like electron or proton, like a cation and anion would be positive and negative charged atoms. When we look at their magnitude, they're directly proportional to the charge. That means if the charges increase, then the magnitude of the force increases, just like we talked about. If the magnitude of the charges decrease, then the magnitude between those two forces decreases. So this is a universal law dealing with charged particles, protons, electrons, cations, and anions. Now the second part of this has to do with the distance. So we focus upon one part, say it's directly proportional to the magnitude of the charges, and then the second part says we're going to also look at the distance, and so it's directly proportional to the magnitude of the charges, and inversely, meaning they go in opposite directions, to the square of the distance between them. So the square is important because if something's cut in half distance-wise, it's actually going to affect the force by a factor of 4. If a distance is cut into a third, it actually affects the force by a factor of 9 because it's squared. It even increases the magnitude so much more than what the charges do. So if we got an atom, it's got a nucleus with protons, and it's got an outer shell of electrons that are negative, we can talk a little bit about attraction between those two. We can say if the distance increases, then the attraction force decreases because the distance gets a little bit further. And so that's when it comes to the size of the atom is really important in explaining some of these characteristics that you're going to explain to me and to your classmates later on. Question. So Coulomb's law, most everybody in here will to use Coulomb law in a way in which to explain their characteristic they're looking at. Okay, it's going to be a kind of big portion of what they're going to take a look at and explain. Okay, so everybody has a periodic table, and on the back of the periodic table you have this thing called Atomic Radii, and it'll tell you what the atomic radii is for every element on there that you want to know the size of. Some of them they don't show would be ones that are radioactive, that are harmful, like francium. They won't tell you it because it's very unstable and very radioactive, and there's just something they're not going to be able to measure. Okay? So looking at your periodic table,
January 5th.
find atomic radii on the back. If you look at your key, the bottom, it tells you a bunch of different characteristics about that particular atom. And one of them is atomic radius, and it's measured in angstroms. An angstrom is like 10 to the minus 10th. It's kind of like a nanometer, but 1/10 the size of a nanometer. So there's 10 nanometers in an angstrom. Okay? So it just gives you radii size in angstroms. What I'd like you to do, only look at the main group elements, groups 1, 2, and then 13 through 18. And I want you to go down, pick a group. Okay, somebody pick group 15, somebody will group 17, somebody will pick group 18, so on and so forth. Go down that group, look at atomic radii, and tell me what kind of pattern or trend do you see for atomic radii down a group. And you can look at multiple groups. Say I want to look at group 1 and 14. I look at both of them, see if I see a trend. What's the trend when we take a look at the size of the atom? Increases, right? There's only one place in the main group elements that it doesn't increase. What group is that? Group 13, the bottom two. Okay, it stays the same, indium and thallium. So that's the only kind of flaw in my statement. And so I'd have my board, and I'd say atomic radii, and then I'd say group trend. And then on it I'd say the group trend for atomic radii in main group elements is to increase in its value. Okay? And then what would I do to prove that to somebody? Would I just leave it at that, or would I give some more additional information?
Give an example.
Give an example of a group. I'd go down a group and I'd say, this group 1, starting with hydrogen going down to cesium, has this characteristic. And so that's what I would do, is I'd say, all right, hydrogen's 0.53 angstroms. Okay, lithium is 1.67. See how these values all increase going down. And I might put 2 groups there. And then up above I'd label it. I'd label angstroms, and that represents distance or radii. Another thing I might do to prove my point is to draw some atoms out based upon the different levels that are being filled by electrons. So I draw hydrogen out, it has the 1s1. Then I draw the lithium out, and it has the 2s1. And then sodium has a 3s1, and potassium has a 4s1. Then I would take that information and try to come up with a reason. Why does the atom get bigger as you go down the group? And you would say, because what? The mass does increase. You're right, but that's the protons, and that does not indicate the size. Because more sublevels, but the main thing is that every atom, as you go down the group, adds on an additional level, right? This is level 1, level 2, which is farther than a level 1. Okay, level 3, level 4. Does that make sense? So like on this board I'd say, the reason that atoms increase in size down a group is because as each atom as you proceed down a group adds on a extra principal energy level. And then give examples of that. That hydrogen has level 1 electron, where lithium has a level 2 electron that is farther away. Okay? Alright? Now, would we use Coulomb's law to explain this behavior? Coulomb's law would say, hydrogen has 1 proton, 1 electron. Cesium has 55 protons and 55 electrons. What happens to the charge in Coulomb's law that kind of goes against that reasoning? So if you said, oh, it's because of Coulomb's law. Because as you increase the charges for electrons and protons, that causes the atoms to get bigger in size. That doesn't make any sense, does it? According to this law, what should happen? If there's bigger charges, what do you know about the force? Greater force. If there are greater forces between those sections, what do you think is going to happen in the attraction between those two sections? They should pull together, right? They should get closer and closer and closer, and that is not happening here. That is not taking place in this example. Okay? So you would not use this idea. The only way you could use this idea would be this. These negatives are repelling. So as you get more and more electrons in a certain area, it goes 2, 8, 18, 32. If you get more electrons in an area, what will they tend to want to do? As you get more and more of them in a certain area, they will tend to what? They're the like charges. They'll tend to want to repel, right? Get a bunch of people that don't like each other in a room, they're going to, you open the doors, they're going to get away from each other. Okay? That's what these electrons want to do also. If you get more and more of them together, they're going to want to repel. So Coulomb's law you could use in that aspect if they're not looking at like charges. Okay? Now, we're going to look at period trend tomorrow real quick. Okay? And then I'm going to give you definitions for some different things you guys will have to look up starting on Thursday.